In this video, we're going to take a look at power series. Power series are something that we've already dealt with without using the term power series. Back at the very beginning of talking about sequences and series, I mentioned the idea of a Taylor series, which is sort of the end goal of what we're building towards. They will take the form of what's called a power series. And in fact, we already dealt with a lot of power series in the last section. We were talking about ratio tests in particular, but root and ratio tests as well. So we've already talked about these. Let me show you exactly what they are. So we've already seen these. Power series is something that takes the form of the following. So power series are, we take our sum from, in this case, I'm going to start with n equals 0 to infinity. And it just has some Cn, some coefficient, times x to the n. They're basically what we were calling infinite polynomials. So this would look like some C0 times x to the 0 being a constant, the number 1, plus C1 times x to the first power, plus C2 times x squared, plus C3 times x to the x cubed, plus C4 x to the fourth, and so on. So again, the c's just represent some coefficients, and you can see that we essentially wind up with a polynomial that is an nth order polynomial, and we're letting n go all the way up to infinity. So it becomes basically an infinite polynomial. It turns out that we can center a power series at a point of our choosing. And the way that we're going to do that is the following. And because this will be a useful skill when we start constructing Taylor series, sometimes we'll want to center them around a point of interest. So we can center one of these things and we can call the point that we're going to center it at x equals a. So I'm going to center it at the point A of our choosing. And by doing that, what we would get is a sum that looks like this. The sum from n equals 0 to infinity of c to the n x minus a to the n. So this will basically center it at the point A. It'll center our series there. And we would wind up with something that looks similar to what we had before, but all the x's would be replaced with x minus a's. So we would get, in this case, c0 plus c1 times x minus a plus c2 times x minus a squared, and so on and so forth, all the way up to infinity. So these are series, just like the ones that we've been looking at, and the main question that we've had up until this point is, does this series converge, or does it diverge? And again, the whole point of that is we eventually want to represent functions using an infinite series, using one of these power series. But if our power series doesn't converge, then it's not going to be able to represent a function. It's not going to converge to that function. So we're only going to have use from a series if that series converges, and indeed if it converges to the function that we're trying to approximate. So we want to know if these converge. Not even if, rather when these converge. They will sometimes and they won't sometimes. Okay, so let's talk about the convergence of power series. There are three things that can happen when we talk about the convergence of a power series. So there are three possibilities. Possibility one is that the series converges only at the point x equals a. If we're trying to approximate a function, potentially our series will only actually approximate that function at that one single point. That's not a very good outcome. So possibility 1 is basically that it doesn't converge to the function that we're hoping it does. So the series converges only at one single point. Let me write that. The series converges only at the point of interest, at x equals a, the point that we're centering it on. A second possibility is that it converges for some finite region. So the way that we're going to phrase that is there is a real number, and we'll call this number r. It's going to be positive, and we're going to call this thing the radius of convergence, hence the use of the letter r. Such that the series converges basically whenever the distance from the point A is less than this value r. So, and we're going to say it converges absolutely for absolute value of x minus a. So absolute value of x minus a is just basically the distance of x of our choosing from a. We're taking the absolute value, so it's positive, is less than r. And diverges for absolute value of x minus a greater than r. So this is again a complicated way of writing that we're just saying r is going to be the radius, a distance out in either direction from the point that it's centered at, that this thing converges on. So if r is equal to 2, and we center this thing at the point a equals 3, then that means that our series converges 2 to the left and 2 to the right of that point 3. So down 2 to the left would be at 1, 2 to the right would be 5. So it converges over the interval from 1 to 5 if our radius is 2. So that's the idea. That's all this one is suggesting. There's a finite radius of convergence. And the third case is that the series converges absolutely everywhere. So for every single possible value of x. So we can apply the idea of this radius to all three cases. So the radius of convergence to all three cases. In the first case, when it converges only to a single point, basically what we're suggesting is that that radius of convergence is 0. So in case 1, let's write that a little better. In case 1, our radius of convergence is 0. In case 2, the radius of convergence is going to be some constant that's positive, but finite. And in the last case, you can think of r as basically being, and again, abusing notation a bit here, can't be equal to infinity, but that's the idea. We have an infinite radius. The set of all the values for which our power series converges is going to be called the interval of convergence. So it's related to the idea of the radius of convergence. As I mentioned a minute ago, if our series is centered at x equals 3, so the value of a is 3, and the radius of convergence is 2, that would mean it would converge from 2 to the left of 3, which is 1, all the way up to 2 to the right of 3, which is 5. And our interval of convergence would be from 1 to 5. So we're going to call that set of values for which the power series converges it is called the interval of convergence. And you'll see these terminologies, the radius of convergence and the interval of convergence, in your homework. So let's take a look at some examples. And that's really going to be kind of the main thrust of the rest of this lecture. Is just going to be doing a bunch of examples of how can we compute the radius and or interval of convergence. So let's look at some examples. Let's try this one. So what is the radius of convergence for, and let's do a few of these. So let's do part A. Let's do the sum from n equals 0 to infinity of n factorial times x to the n. And so if we looked at the individual terms in this thing, we could write them all out. But we want to know basically when it converges or when it doesn't converge. We can probably try to get a sense of kind of what's going on by just looking at the behavior of the functions themselves. Pretty much these functions are both growing, so we're summing a bunch of terms that are getting larger and larger and larger. This term has the potential to not grow, but this one is growing no matter what. N factorial is going to grow as n increases no matter what. X to the n has a potential to get smaller as n increases, but that'll only happen if x, the value of x here, is less than 1. So if x is less than 1, or even more than that, between -1 and 1, then we basically have an exponential with the base being less than 1. This will eventually decay to 0, but this is going to infinity. And in fact, factorials are larger. If you remember our hierarchy, factorials grow faster than exponentials. And what we'll see is, in the end, this is going to beat out this growing, is going to beat out this term shrinking, even in the rare cases where this term is actually shrinking. And so I would expect that this really isn't going to converge. At best, we're going to get it to converge maybe for a single point. And that's what we'll see. But let's take a look at the actual process to get to that point. But I want you, again, whenever possible in these, start to try to build up your intuition. Think about the interplay of the functions that you see, and try to get a guess for what you think is going to happen before you actually verify it, because having that intuition ahead of time will make the whole process a lot easier. So what I'm going to do is I'm going to call this term our a sub n, and I'm going to use the ratio test on this. And I'm going to use the ratio test because the ratio test is great to some degree on exponentials, but especially on factorials. So let's do the ratio test to see if we can figure out if this thing converges or not. So the ratio test, you'll recall, says we need to take the limit as n goes to infinity of the ratio of basically our an plus 1 on top over a sub n, absolute value of the whole thing. And if this is less than 1, if we can get this limit to be less than 1, then it'll converge. So that's what we're trying to find. Is it possible, and or for what values of x can we get this thing to converge? So keep that in mind. I do want to point out that really the difference, because maybe this wasn't clear, these power series look like stuff that we've been talking about, but I want to make it really clear. We have an x in all of these. In the other series that we've been looking at up to this point, we've pretty much only had an n show up in here, right? It's some function of n. And when we did the integral test or certain comparison tests, we then maybe compared it to a function that had an x in it. But when we've been looking at series so far, it's only had n and constants. Now we have this additional variable x, and this is what makes it a power series. And this is what makes it possible that maybe for some values of x, it'll do one thing, and for other values of x, it'll do something different. So these are indeed different from the stuff that we've been looking at for the last several sections. So just keep that in mind. This x part is pretty new. So let's take a look at the ratio test for this particular example. For this particular example, our ratio test says that I'm going to take the limit as n goes to infinity of plug in n plus 1 for these. So I'm going to have n plus 1 factorial times x to the n plus 1 power over, on the bottom, n factorial x to the n. And again, we're taking the absolute value. So, if we cancel, remember how the factorials cancel. You can think of this as n plus 1 times n minus 1, yada, 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 all the way down to 1. So, n plus 1 times n minus 1 times n minus 2, dot, 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 down times 3 times 2 times 1. And below that, we have n factorial, which looks like the exact same thing, except for the n plus 1 term. So I'm going to erase this in a minute, but we get cancellation of those two terms, those two terms, those two terms, and so on all the way down to the bottom. And all that's left out of this, when I take n plus 1 factorial and I divide it by n factorial, all I'm going to be left with is n plus 1. So just a quick reminder of where this simplification is going to come from. Let me delete that real quick. But what I've got now is the limit as n goes to infinity of n plus 1. That's what the 2 factorial term simplified to. And similarly, what's happening here, x to the n plus 1 is x times x times x times x, n plus 1 times. And on the bottom, I've got x times x times x, n times. So I have one extra x up here. We can do our cancellation, and I'm going to get an extra factor of x left over in the numerator here. So this is it. This is what we've got here. And if we try to figure out what the behavior of this is, so absolute value or not, it doesn't really matter in this case. But if we try to figure out what the behavior of this is, n plus 1, this thing is going to infinity. X, we can think of, again, as far as n is concerned, x is just a constant. Are there values of x where this thing isn't going to go to infinity? So if x is 1, doesn't matter. This thing's going to infinity. This will go to infinity times 1. Still going to infinity. If x is 2, still going to infinity. If x is 0.1, well, I have infinity times 0.1. That's still infinity. There are no values of x for which this thing isn't going to go to infinity, except potentially x equals 0, in which case we will have basically this n plus 1 times 0 will be having a bunch of zeros over and over and over. So 0 times infinity. And the question is who wins? And in that case, the 0 will win. So this thing is going to diverge off to infinity unless x is equal to 0. So because it diverges, except when x equals 0, the radius of convergence is r equals 0. It only converges for that one single value, so the radius of convergence is 0. You can't build any buffer around this point and get it to converge. So that's exactly what I said we would expect at the very beginning, that for the most part, both of these functions are going to be growing anyways, even in the rare case that we get a value here for our x, where this thing is going to be shrinking. So if x was less than 1 and this thing was shrinking, this term is still growing faster than this term is shrinking, and we will get divergence. The only place we don't get divergence is when x itself is 0. If x itself is 0, then we've just got a bunch of zeros here, and we're doing the sum of an infinite number of zeros. Okay, let's do another one and see how this goes. So part B, let's try a different one. Let's do the sum from n equals 0 to infinity of x minus, oh, come on now, x minus 3 to the n over n. So again, this is our a sub n term. Just like before, I just want to do pretty much, in this case, the ratio test. Again, because I have some exponentials here, we could do the ratio test on this thing to try to figure out what the behavior is going to be or where this thing might converge. So does this thing converge? Is it possible to make this thing converge? So I'm going to do the ratio test again. And again, just to remind you, let me just write it out generically here again. The ratio test says we take the limit as n goes to infinity of an plus 1 over an, and if it's less than 1, then it converges. If it's greater than 1 or equal to 1, if it's greater than 1, it diverges. If it's equal to 1, then the test is inconclusive. So let's go and look at this more carefully and figure out what's going to happen. So in this case, when we actually look at our specific example, we take the limit as n goes to infinity of our an plus 1. That means on our numerator, I'm going to get x minus 3 to the n plus 1 power over n plus 1. And then I'm dividing that by our term in the denominator should just be a sub n itself. So x minus 3 to the nth over n. So there's what our ratio looks like. We will do all the cancellation that we can. I have x minus 3 to the n plus 1 power and x minus 3 to the nth power. Most of those will cancel. All that will cancel is, or the only thing that won't cancel is the one remaining factor of it that I have up here. So I'll wind up with a factor of x minus 3. And then similarly, I've got this n plus 1 over n on the bottom. In that case, there's nothing special necessarily that we can use to try to factor this. I'm going to wind up with an n plus 1 in the bottom of our numerator and an n in the bottom of our denominator. One way to make this, maybe this would make it a little easier to see, is again, whenever we have a ratio of two fractions, it's often easier to write it as a product. So let me just add one interim step here. Now we get all of our cancellation of all of these terms, cancel with all of these except for that plus 1 term. But there's nothing to cancel. N over n plus 1, I can't cancel the n's. So we're going to wind up with that fraction remaining. So this is going to give us the limit as n goes to infinity, absolute value, one factor of x minus 3 survives, and I have n over n plus 1. And we're taking the limit as n goes to infinity. As far as the n is concerned, this x minus 3 is a constant. We can pull that thing outside of the limit, and that's what we'll do. So I'm going to have the absolute value of x minus 3, pull that outside of our limit, because the limit only deals with n, and we've got the limit of n over n plus 1. Again, still in our absolute values if we want there. Doesn't matter because n is only positive anyways. But what do I get in this limit? All I need to do is look at the highest powers of n to the first over n to the first. The coefficients are both 1. The ratio of them is 1. As n gets really large, n and n plus 1 are basically indistinguishable. This whole thing is going to 1. So I'm just going to get absolute value of x minus 3. So this is our limit that we just got from our ratio test. And I want to know, when is this less than 1? Because when it's less than 1, then it converges. So When is it less than 1? Actually, so it's easier to see, let me erase it over here and we'll rewrite this down here. So I'm asking, when is the absolute value of x minus 3 less than 1? And now we can figure out basically how this is all going to work. So in this case, you can see, if you think about the way this is set up, we have this term, which you can think of as being centered at x equals 3, right? When I plug in x equals 3, this whole term will go to 0, which is definitely less than 1. I can make this value of x be as large as 4, up to but not including 4, and that would make this number in here be 1, absolute value of 1 less than 1. So I can't let it be equal to 4, but I can get up to but not including 4. Similarly, because of the absolute value, I could go in the negative direction. I could get this thing to be a value of up to but not including -1, and the absolute value will make it positive. And we can deal with that as well. So in that case, if I let x be 2, so positive 2, 2 minus 3 is -1, and that's sort of my other boundary. So essentially what I'm suggesting is, whenever you have an absolute value, you can always rewrite this. This is basically the same as saying -1 less than x minus 3 less than 1. Turn a single inequality with an absolute value symbol into a double inequality. We need the stuff in here to be greater than -1, but also less than +1. So greater than -1, less than +1. And then we add our 3 to both sides. So if you add 3 to all the different, every single term, so +3, +3, +3, now we wind up with 2 less than or equal to x less than, and not less than or equal to, I'm sorry, 2 less than x less than 4. So this is our interval of convergence, and our radius of convergence is 1. We can go 1 in either direction from this. So our radius of convergence is 1. And the interval from 2 to 4, exclusive, right, excluding the endpoints, is our interval of convergence. And on the exam, I won't care. You can write your interval of convergence this way, or you can do interval notation. On the homework, I think they want you to use interval notation. It's been a while. I can't remember what form they'll want. But this is the idea. So what you're going to see is a lot of these problems are going to involve the ratio test and sort of tweaking that ratio test to figure out what the radius of convergence is. So let's do some more. Let's keep practicing. For the third one, I want to do the sum from n equals 0 to infinity of, let's do like an alternating series type 1, where it does -1 to the n, x minus 1 to say the 2n, over 2n factorial, and it's the whole 2n that's being factorialized. So same thing, this one involves some factorials. It involves sort of an exponential with our base x here. And we want to, in that case, use our ratio test. I'm not going to write it out again. Let me just say, let's use the ratio test. So I'm not going to write it out generically. Let's just do our specific one here. I want the limit as n goes to infinity of the absolute value of this thing with n plus 1 as my numerator, and then the same thing with n plus 1, or sorry, with just n is my denominator. So -1 to the n plus 1, x minus 1 to the 2 n plus 1. Don't forget to put your n plus 1 in parentheses, over 2 times n plus 1 factorial. So that's our numerator, and then our denominator is just the original one. -1 to the n, x minus 1 to the 2n over 2n factorial. So here's our big ugly mess. Do the same thing that we did before. Instead of writing a fraction divided by a fraction, let's multiply by the reciprocal to get -1 to the n plus 1, x minus 1 to the 2 times n plus 1 over 2n plus 1 factorial times the reciprocal will be, I'll get a 2n factorial on top, and on the bottom I will get -1 to the n, x minus 1 to the 2n. So there is this thing just rewritten. Instead of fraction divided by a fraction, it's that fraction times the reciprocal of the other fraction. And we can cancel away. So this is where we've got to be careful. Just make sure that you're doing your cancellation correctly. The algebra is always where people screw these things up. So first things first, let's look at the -1. The fact that we're dealing with absolute values here means I don't care about this term regardless. Whether this winds up positive or negative won't matter because I've got the absolute value. So if we look at this though, I would wind up with a -1 to the n plus 1 over -1 to the n. It leaves me with one factor of -1. I would get a factor of -1, but again, the absolute values mean I don't care about that. So let's leave that term off entirely. Don't care about that. What I do have still is, let's see here, we're going to have this term over this term. So x minus 1 to the 2n plus 1, if you want to think of this, maybe it would be easier to come back up here and rewrite this as actually distribute the 2 through and write this as 2n plus 2. It'll make it a little bit easier to see what's going to cancel. The 2n and the 2n will both cancel, but that leaves me with 2 extra factors of x minus 1 in the numerator. So I'm going to wind up with an x minus 1 squared in the numerator. So I've taken care of these terms. I've taken care of these terms. Now let's take care of these ones that involve factorial. And same thing, I can rewrite this one down here. Maybe it's easier to rewrite this as simply 2n plus 2 factorial. So what you can think of is this one is 2n plus 2 times 2n plus 1 times 2n times ... Everything from here over is simply 2n factorial. So these parts will all cancel with this part, and what I'll be left with are just these two factors. So that's what I'm going to write down here. 2n plus 2 times 2n plus 1. Those are all the terms that didn't get canceled. And if we want, let's keep our absolute values there for the time being, but it's not going to really matter. These terms are always going to be positive because n starts off at 0 and goes to infinity, so n is always non-negative, so these are both going to be positive. And this term here is being squared, so it's also always going to be non-negative. So I don't actually need the absolute values at this point because of this square here on the x terms, but it doesn't really matter. So now that I've got this, let's get rid of those absolute values in this next step. This term, the x minus 1 squared, as far as the n is concerned, this is a constant, so I can pull out that outside the limit. So I've got x minus 1 squared sitting outside of the limit, and I've got the limit as n goes to infinity of 1 over 2n plus 2 times 2n plus 1. What is this limit? Well, this is going to go to infinity. This is going to go to infinity. The product's going to go to infinity, basically like n squared, essentially. In this case, 4n squared would be the dominating term. So because the denominator is going to infinity, the overall fraction is going to 0. This limit is 0. And 0 times whatever this x thing is still going to be 0. Doesn't matter that it's times x minus 1 squared. This is always less than 1. So for all values of x, pick any finite value of x you want, you multiply it by 0, you're getting 0, and it's going to be less than 1. So this is a case where our radius of convergence is infinite. Infinite radius of convergence, which is a little more notationally correct than writing r equals infinity. Infinite radius of convergence, which means similarly that our interval of convergence is from negative infinity to infinity. Is the interval of convergence. And I, again, probably could have suspected that looking at this thing and just thinking in general, what's the behavior, right? Really, the behavior is going to, in some cases, depend on what x is. But either way, even when x is growing, or when x is such that this term is a growing term, even if I didn't have the negative 1 to the n, forgetting that piece. But if I have an exponential here, right, pick a value of x to give us our base value, and we're just letting n go to infinity, so I've got some number to the 2n power. Even though that exponential is growing, 2n factorial is going to grow faster. So I'm going to have a smaller function over a larger function. The overall ratio is going to eventually go to 0. We should expect convergence. And that's exactly what we saw when it was all said and done. So I want to do 2 more examples. And the first example I want to look at is similar to what we've just been doing. So, oops, come on. So, first example, there we go. I want to find the radius and interval of convergence of a function, but I want to worry about the endpoints. So I'm going to care about the endpoints of that interval of convergence. So on an example like the one we just did, where the interval goes from negative infinity to infinity, it doesn't matter. But when we get a result like the one that we did up here, from 2 to 4, how do we know whether or not we can include the 2 and the 4 as part of that interval, or whether they need to be excluded from that interval? So that's what I want to take a look at. Okay, so let's look at this example. I want the sum from n equals 1 to infinity of x minus 2 to the n over n times 5 to the nth. So as you can see, in terms of x, if we have this thing representing some function, this thing is centered at x equals 2. So this thing is centered at x equals 2. That'll give us some insight. When we find our radius of convergence, for example, we would expect that radius of convergence to construct the interval of convergence, it'll be centered around x equals 2. To do this one, we're going to use the ratio test again. We haven't used the root test on any of these, and the root test doesn't come up quite as much as the ratio test. But if, for example, instead of having 5 to the n here, if instead I had n to the n, that would be an example where using the root test might be more useful. So just keep that in mind. Really, root test comes up when you have some function of n raised to a power of n, if that makes some sense. So, or if you have the whole thing raised to some power of n at the very end, that's when you have when it makes sense to use the root test. But in this case, I'm going to use the ratio test again. The ratio test for this one is going to look like the following. So here is our a sub n. So our ratio test is going to be the limit as n goes to infinity of an plus 1, which will look like x minus 2 to the n plus 1 power over n plus 1 times 5 to the n plus 1. So there's our an plus 1 term, and we're dividing that by an itself. So here's our big ugly fraction of fractions. We will, instead of dividing by a fraction, we'll multiply by the reciprocal to get the following. So we're going to have x minus 2 to the n plus 1 over n plus 1 times 5 to the n plus 1 times n times 5 to the n over x minus 2 to the n. And you're going to notice a pattern. We're doing almost all the problems wind up looking like this, and we just try to make sure that we don't make any stupid mistakes when we do our algebra and our cancellation here. So let's start with these terms. X minus 2 to the n plus 1 over x minus 2 to the n. I have n plus 1 factors of x minus 2 here. I only have n of them here, so I have 1 extra on top. When it's all said and done, I'm going to wind up with 1 extra factor of x minus 2 in the numerator. When it comes to the 5 to the n and 5 to the n plus 1, I have 5 times 5 times 5 n times, so 5 times itself n times here. I have 5 times itself n plus 1 times here, so I have an extra 5 down here relative to up here. I'm going to wind up with an extra 5 in the denominator. And then lastly, the n and the n plus 1. And there's no simplification I can do with those. Simply, it's going to be n on top, n plus 1 on the bottom. And we've got our absolute value symbols. So that's what this thing simplifies to in this case. Again, the n terms here, they're never going to be negative. It's really just this term that I need to worry about being negative. So I'm going to apply the absolute values just to the x minus 2 and pull that outside of my limit. So I'm going to have the absolute value of x minus 2. That's outside of the limit. And then inside the limit, it's n over n plus 1. And I don't need to worry about the absolute value symbols because, again, n starts at 1 and it's going to infinity. Both of those terms are positive anyways. What is that ratio, or what is that limit going to be? That limit is going to be 1 again. And so I'm going to just get x minus 2 times this whole limit, which is simply 1. So we just get x minus 2. Oops, I missed my factor of 5. So this is very important. I can't skip that factor of 5. Let me go back and erase here. That factor of 5 can totally get pulled outside of the absolute value symbol as well because it has, again, no bearing on n. So it's not x minus 2 that I'm going to pull out. I'm going to pull out x minus 2 over 5. There we go. So that's the piece that I meant to pull out, times n over n plus 1 here in the limit. And again, now this is the thing that's going to 1. And we wind up with simply x minus 2 absolute value over 5. And the 5 itself is obviously positive, so I'm going to just put the absolute value up on the numerator. So that's what we've got. And I want to know, when is this less than 1? Because that's when the ratio test indicates convergence. And remember, when the ratio test gives you that it's equal to 1, then the ratio test is inconclusive. And so that's what we're going to need to worry about, is to figure out the endpoints. But for now, let's just worry about when it's less than 1. So I have x minus 2 over 5 less than 1. I can rewrite that as the absolute value of x minus 2 less than 5 if I multiply both sides by positive 5 here. And then I can convert that, getting rid of the absolute value symbol. I can change it that I want basically x minus 2 to be between negative 5 and 5. And that will give me, in this case, now adding 2 to both sides of this to get x by itself, we'll get negative 5 plus 2 less than x less than 5 plus 2, which finally gives me, when it's all said and done, negative 3 less than x less than 7. So in this case, the radius of convergence is 5. We figured that out basically right at this step. Here's going to be, whenever you get the x minus some constant in absolute values by itself, whatever's on the other side is always going to be our r. So the radius of convergence is r equals 5. And the interval of convergence is going to go from negative 3 to 7, but I don't know about the endpoints. So let's check the endpoints of the interval of convergence. So I need to check negative 3 and positive 7 separately. So let's start what happens when x is equal to negative 3. So when x is equal to negative 3, what we'll get, coming back up to our original problem, what I'm suggesting is we found that this thing is going to converge. Basically, when x goes from negative 3 up to 7, not including those endpoints, what happens at those endpoints? So let's plug in x equals negative 3. If I do negative 3 here, I will get a total of negative 5 inside my parentheses. So I'm going to get the sum from n equals 1 to infinity of negative 5 to the n over n times 5 to the n. There we go. So all I've done, again, is gone back to the original series. Zoomed in a little too much there. Gone back to the original series and plugged in x equals negative 3. And that's what gave me this negative 5 right here. I can rewrite this as the sum from n equals 1 to infinity of negative 1 to the n. Right? I can split this up into a negative 1 times 5. So I've got negative 1 to the n times 5 to the n, if I can stop hitting this erase button, over n times 5 to the n. And we get some nice cancellation here. And I wind up with an alternating series that simply looks like this, negative 1 to the n times 1 over n. This thing converges by the alternating series test. The alternating series test said that if you have an alternating series, all you need is for this a sub n term here. Maybe I've already used a sub n, so let's call this b sub n, needs to go to 0 as n goes to infinity. And indeed it does. Normally this would be a p-series problem, right, with p equal to 1, which diverges. But because of the alternating, all that's required is this term goes to 0. And so this part converges by the alternating series test. What happens when we plug in x equals 7 instead? So going back to the original problem here, now I'm plugging in 7 here. I'm going to plug in 7 for this number. 7 minus 2 is going to be a positive 5 to the n in the numerator. So I'm going to get something that looks very similar to what we started off with here, but it's not going to have the negative sign. This is just going to be 5 to the n over n times 5 to the n. Those 5 to the n's cancel, and we get the sum from n equals 1 to infinity of simply 1 over n. This is the harmonic series, the p series with n equals, or sorry, the p series with p equals 1, and that diverges. This diverges by p series test with p equal to 1. We need p to be less than 1 in order, we need p to be greater than 1 in order for this thing to converge, but it's equal to 1 in this case. So that means we got convergence at x equals -3, but didn't get convergence at x equals 7. So what does our interval of convergence look like? So our interval of convergence, we know it goes from 3 to 7, but we include, -3 to 7, we include the -3 because it converged there, and we exclude the 7 because it diverged there. So in interval notation, square bracket on the left because the -3, that endpoint is included, and open parentheses on the right because the +7, it diverged there. That point is not included. So our radius of convergence was 5, and our interval of convergence is from -3 to 7, inclusive of the -3, exclusive of the 7. So this is the idea. This is how we will check the endpoints, and oftentimes it'll boil down to a test that looks very similar to the one that we just did here. You'll see something that looks like this a lot. Okay, let's do one more example. And this example is going to be, in a lot of ways, kind of the most important example. It's different from the stuff that we've been looking at, but it gets at the heart of why we care about these power series anyways. So why do we care about power series? They can represent functions. We can use them to represent functions. So I'm going to give you a function, and I want to figure out, I'm going to give you a function in the form of a power series and try to figure out what it represents. So consider the following. Our f of x is going to be a power series. The power series looks like this. It's the sum from n equals 0 to infinity of -1 to the n, x to the 2n, divided by 2n factorial. And in fact, if we come back here, it's very similar to the one we did right here. It just doesn't have that x minus 1. So instead of being centered at x equals 1, this one is centered down here at the origin, at x equals 0. So here's the function. If we look at the terms, in fact, let me not even do an approximate sign. If we write out the first few terms of this, so when I plug in n equals 0, what are we going to get? I'd get -1 to the 0, which is +1, x to the 0, +1, over 0 factorial. 0 factorial, by definition, is also 1. It's one of those weird things. It's just defined to be 1. And we get, for this first term, we get 1. So again, just note, somewhere off to the side here, 0 factorial equals 1, by definition. So the first term is going to be 1. When I plug in n equals 0, we get 1. Now let's plug in n equals 1. I'll get -1 to the first power, so I'm going to get a minus sign out of this. That means the next sign is going to be a negative. I'm going to get x to the second power, so I'm going to get x squared in the numerator, and in the denominator, I'm going to get 2 factorial. And I'll just leave that written as 2 factorial. Now let's plug in n equals 2. When n equals 2, I'm going to get -1 squared. That's back to a positive, so I'm going to have a plus for this next term. Again, n is equal to 2, so this power is going to be now 4. So I'm going to get x to the 4th power in the numerator. And in the denominator, I'm going to get 4 factorial. And then I'm going to plug in n equals 3. n equals 3 will make this negative again. I'm going to get x to the 6th in the numerator over 6 factorial. And then when n equals 4, the sign will flip back to positive, and I'll have x to the 8th over 8 factorial minus ... So that's what this series looks like when I write out the individual terms. It's a function of x in the form of some infinite polynomial. What function does this represent? Well, one thing that I want to show you is that we can, if we are given a function in the form of a power series, we can apply our normal calculus operations to that function. We're going to assume that this thing is smooth because it's represented by a polynomial, which by definition is smooth. It just happens to be a polynomial of infinite order polynomial. And so that starts to throw things into question. But that's what we're going to assume, that we can just apply our normal calculus procedures to this. So keep this in mind. I want to start off with f of x and write it down again. So I'm just copying what we just wrote, x squared over 2 factorial plus x to the 4th over 4 factorial. Just want to write out a handful of terms here. Minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus ... And we already said we can represent that as the sum from n equals 0 to infinity of -1 to the n x to the 2n over 2n factorial. And let me put that 2n in parentheses. 2n factorial. What I'm suggesting when I say that we can apply calculus to this is I want to know what f prime of x looks like. So first and foremost, I want to figure out what this function represents, and I'm just trying to do some calculus to get some clues about it. One thing you'll notice is every single one of these terms so far has an even power of x, including this constant right here. You can think of it as x to the 0th power. That's a good indication that the function I'm dealing with so far is an even function. That should be a pretty good hint. Might be all you need at this point. But let's check a few other things. What happens when I take a derivative? Well, when I take a derivative of the function, I'm just taking a derivative of this whole thing. I can do it term by term. So what's the derivative of the 1? 0. What's the derivative of this term? So I've got basically an x squared with a factor of -1 over 2 factorial. Well, when I take the derivative, this factor of 2 is going to come down. I'm going to get minus 2x over 2 factorial. The next one will be plus 4x cubed over 3 factorial. The next one will be minus 6x to the 5th over 6 factorial, plus 8x to the 7th over 8 factorial, minus ... And if we simplify this, so I'll keep that 0 there, but let's think about what's happening with the 2 and the 2 factorial. The 2 and the 2 factorial is just 2 times 1. And so I can cancel the 2's, and this really is just going to be negative x over 1. Or I can even write it as 1 factorial if we want. 1 factorial. The next term Oops, and I miscopied this when I did it. It should be 4 factorial in the denominator. I didn't change the constant here, so it should just match this one. But same thing is happening. I'm taking 4 and dividing by 4 factorial, or 4 factorial is 4 times 3 times 2 times 1. So the 4 here will cancel with the 4 here, and I'll just be left with the 3 times 2 times 1, which is 3 factorial. So I'll wind up with plus x cubed over 3 factorial. The next term will be minus. The 6 here will cancel with the 6 and the 6 factorial and leave me with only the remaining terms other than the 6, which is 5 factorial. So I'll get minus x to the 5th over 5 factorial. Same thing up here. This will be plus x to the 7th over 7 factorial minus dot, 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 dot. And so when I try to rewrite what this looks like, you can also think of what's going on here in terms of taking the derivative of this piece. So I'm going to have the sum. The only thing that we kind of have to be a little bit careful about is what happens with the values of n, because again, this is defined right here to have n only be 0 and positive. When we take a derivative, we just need to make sure that we don't wind up with weird like negative powers of n. We may have to fudge the n. So I'm going to leave the n blank for now. Let's do n equals, it's going to be something, and we're going to have it go to infinity. But think about what the result is that we get over here. The negative 1 to the n, that's just a constant. When you take a derivative, that constant just comes through. So I'm still going to have a negative 1 to the n. What happens when I take the derivative of x to the 2n? This is the only term that is being affected, right? I will get 2n x to the 2n minus 1. And all of that is now divided by 2n factorial. And so this is basically just taking the derivative naively. Let's just go back and say n equals 0. The only thing that I want to note is that this gets a little screwy, because when n is equal to 0, what's happening here? Well, we're getting x to the negative first power, and that's not something that we want to have happen here. That basically can't happen, because it would presume that basically if you plugged in the n equals 0 here for this first term here, this term, even though it looks like x to the 2n, when n is equal to 0, it's really just x to the 0. It's really a constant, and the whole derivative of this would wind up being 0 anyways. It's not a function of x when n is equal to 0 anyways. So we need to correct for that. This is why I said we have to be a little bit careful about this 0. So let me just say we need to be careful. This is almost like what we've got over here. You'll notice we did the cancellation where we did the 2n, and we canceled it with the 2n in the 2n factorial. And we wound up with, really, when I cancel this and this, what I wind up with is 2n minus 1 factorial down here. And we need to correct for this by, again, we couldn't let that value of n be 0 anymore, because that's giving us negative numbers. These are not well defined. And the original function when n equals 0 really wasn't a function of x anyways, right? It was just this number 1. So we need to be careful. We need to re-index this thing. And what we wind up with is, in this case, this looks like the sum from n equals 1 to infinity. Because again, when n equals 0, none of these are well defined. When n equals 0, the original value was a constant up here, and we got this term. So we're just going to start at n equals 1, so we start with this term instead of n equals 0, or we started with this term. We don't want to force add in a 0. So this is the first term that we're going to get. So I'm going to get negative 1 to the n, x to the 2n minus 1 over 2n minus 1 factorial, incidentally. Okay, so we took the derivative here, and we got this, and all we needed to do was be really careful, again, about how our indexing is working, because when n equals 0 in the original function, it's not actually a function of x. The whole thing is just a constant for that first term. And we need to make sure that we aren't screwing stuff up when we generically take a derivative of the term, of our a sub n term in the series. Okay, with all of that said and done, what's the point? We took a derivative, we went from a function that had only even terms to now a function that has only odd terms. There's another good indication that might help you figure out what's going on here. We've got a function that's even, its derivative is odd. Maybe that's a relationship that makes some sense to you. Let's take another derivative. So if I take another derivative, we're now taking derivatives of these terms here. So just keep in mind what's going on. The zero term is gone. Forget about it all the way. I'm just going to come down with this term as the first term. When I take the derivative of that term, I've got a negative, and this is going to be, again, just the derivative of x is just 1, and it's over 1 factorial. I have a negative sign. This whole thing is just simply negative 1. What about this term? Well, that's going to be plus 3x squared over 3 factorial. And the next term will be minus 5x to the 4th over 5 factorial plus 7x to the 6th over 7 factorial minus dot, 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 dot. So let's clean this up a little bit. I've got negative 1. I'm going to cancel the 3 and the 3 in the 3 factorial and wind up with just a 2 factorial. So this is really x squared over 2 factorial. The next term, I'm going to cancel the 5 in the numerator with the 5 that shows up in the 5 factorial. So this is just going to have the 4 times 3 times 2 times 1 left. It'll be 4 factorial. And then same thing in this last term. It's just going to be x to the 6th over 6 factorial minus dot, 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 dot. And if we look at this, what is this thing going to look like? Well, I can come back. We could take the derivative over here, and again, just make sure that we don't do anything too crazy and get any weird results. But this, if I took the derivative, we have the sum from n equals 1 to infinity of negative 1 to the n, because that's a constant, over the 2n minus 1 factorial, because that's a constant. And this is the only term that would be effective. We'd get a factor of 2n minus 1 times x to the 2n minus 2 as the power. But we can clean this up. I can cancel part of this with part of this. So cancel this with this. And this is now just going to leave me with basically a 2n minus 2 factorial term. This looks a little bit wonky, but if I re-index it, again, instead of starting at n equals 1, if we re-index it to start back at n equals 0, what I've got is negative 1. Think about what happened. When we're re-indexing, what it means is we're basically shifting how n behaves. So here when n equals 1, which was our starting value, we got negative 1 to the 1. Now I want to get that same behavior. I want negative 1 to the first power, but I want that to happen when n equals 0 instead of when n equals 1. So all I'm doing is relabeling basically how I'm treating n. I want to get the same result that this one gave me when n equals 1 in this one when n equals 0. And that means that the power up here needs to, in this case, be n, you can think of it as n plus 1, right? And that way, when I plug in n equals 0, n plus 1 will have the same effect as having n equals 1. And I just want to do that for every single one of these terms. So in a sense, what you can think of is this term, for example. When I plugged in n equals 1, what did this one, or sorry, yeah, when I plugged in n equals 1, what did this give me? It gave me x to the 0th power. What do I want that to look like now? Well, I can just have this be x to the 2n. That'll give me 0th power. Similarly, down here in the denominator. When I plugged in n equals 1, what did I get in the denominator? N equals 1 gave me 0 factorial. If I want 0 factorial down here, I can just do simply 2n factorial. So this, let's see how this compares. basically what I'm suggesting is that when I plug in n equals 1 in this case, and when I plug in n equals 0 in this case, I want them both to spit out the first term that we got over here. I want them both to spit out basically the negative 1. So let's just verify that that happens. When n equals 1 here, I plug in n equals 1. This negative 1 to the 1 is going to be negative 1. There's my negative sign. And we will plug in n equals 1 over here, and I will get this power to be 0. And similarly in the bottom, I'll have 0 factorial. So 0 as my power up here makes this a 1. 0 factorial is also 1. And I'd simply get a negative 1, which is the number that we got here. Do the same thing down here. Now when I plug in n equals 0, I'll get negative 1 to the first power. I will get x to the 0, and I'll get 0 factorial in the denominator. I'll get the same term. Now let's go to the next term, n equals 2 up here. So when n equals 2 up here, I should get this term. When n equals 2, I'm going to get negative 1 squared, which is positive, which checks out over here with the plus sign. When I plug in 2 to this term, I'm going to get 2 times 2 minus 2, so I'm going to get x squared. That part checks out. And I'm going to wind up with, on the bottom, when I plug in the 2, I'm going to get, again, 4 minus 2, which is 2 factorial. And that's what we wound up with. The 3 and the 3 factorial canceled, and we got this term. So this, when I plug in n equals 2, gives me this term. I want the same thing to happen down here when I plug in n equals 1. When I plug in n equals 1 here, I'll get negative 1 squared, so it's positive. I'll get x squared, exactly what we got, and I'll get 2 factorial, exactly what we got. All I'm suggesting is when you re-index, you can make something that's a little bit more complicated look a little bit more simple. And that's all we've done. So, long story short, what was the whole point of this? I want to compare these. How does f of x compare to f double prime of x? Well, if I look at their expressions, so if I look at the individual terms, I'll notice I had a 1 here, but now it's a negative 1. I had a negative x squared over 2 factorial, now it's a positive x squared over 2 factorial. I had a positive x to the 4th over 4 factorial, now it's a negative x to the 4th over 4 factorial. F and f double prime, so f of x is equal to the negative of f double prime of x. They're opposites of one another. What is a function that when you take the second derivative gives you back the original function but with a sign change? And that function is also even. All of these are indications. So the function is even. And equal to its, or to the opposite, rather, to the opposite of its own second derivative What is f of x? It's cosine of x. These are the indications that we're seeing. And sure enough, this is going to be the power series representation of cosine of x. And here's the justification for that. But again, the main point of doing this is to try to think about the features of functions that you know. So things having to do with symmetry, things having to do with their derivatives or multiple derivatives, and think about how that might relate when we start taking derivatives. And then secondly, recognize that when we take a derivative of a power series, you can do that derivative term by term by term. And when you do simplification, you can also do it on the power series representation. But when you do it on the power series representation, you do need to be very careful of the indexing, because some of these terms that may look like functions of x, for example, when n equals 0, is really a constant. And it can be misleading to simply just take the derivative and forget about the fact that, if I left this as n equals 0 here, it turns out we don't actually get something that's exactly equal to the derivative, because it'll give me a weird term, or that term is negative 1 power, right? I can't say that the derivative of x to the 0, you can't do power rule on this. You can't say this is 0x to the negative 1 power, and it'll give you some weird results, right? That's the kind of weird thing that's going on here as well. It's giving us this extra term, and so oftentimes it's nice to re-index so that we see it a little bit more nicely. Anyways, long story short, here's a little bit of exercise in re-indexing, but the main concepts are if you can represent a function by a power series, then you can represent the derivatives of that function by the derivatives of that power series. And so that's going to be the main takeaway. This is going to be a tool that we use a lot going forward. And starting in the next section, we will look at power series representations of functions with the idea of convergence in the back of our minds so that we can ultimately build the tool of Taylor series, where we can build functions, build polynomial representations or polynomial approximations of functions that are transcendental functions using only algebraic pieces.